In this video, we're going to continue our attempt to look for laws which govern the way in which sets behave when they're combined using unions and intersections and complements. So in fact, the specific thing we're interested in is called De Morgan's laws. And you can see De Morgan's laws written at the top of the screen here. So the setup for De Morgan's laws is that you have two sets A and B, which are subsets of some larger set omega. And I'll remind you of the notation we used when in our first video when we talked about subsets and membership and complements. And that was that when you had a subset A of a set omega, then the complement for A in omega, which you wrote as A to the C, was defined to be the set difference omega take A. So that is every element of omega which is not an element of A. So what De Morgan's laws say then is if you have these two sets A and B, which are subsets of a larger set omega, then firstly the complement of A union B is equal to the complement of A intersect to the complement of B. So that's the first of De Morgan's laws. And then the second of De Morgan's laws says that the complement of the intersection of A and B is the complement of A union the complement of B. So before we get into a proof of one of these, let's just take a quick look at what I've got over on the right of the screen there. There is a Venn diagram in which the big rectangle is supposed to represent this larger set omega of which A and B are subsets, and the grey shaded area is, well, it illustrates one of De Morgan's laws, and as usual you should pause the video now and figure out which one of those two laws is being illustrated. Okay, I hope you did it. Of course, the law that's being illustrated here is the first of De Morgan's laws. The grey shaded area is the complement of A union B. It's everything which is in omega, but which is outside the union of A and B. And you can also convince yourself that it is the area you get if you shade everything which is outside A and outside B. In other words, the intersection of A complement and B complement. And the fact that those two areas coincide is exactly the fact that the first De Morgan's law is true. So let's have a go at proving the first of these De Morgan's laws without using a picture, but with trying to make a formal argument to prove it. If you'd like to see an argument for the second one, you should look at the typed notes for this video. So let's prove part one. Okay, whoops. So proof of number one. All right, how do we do this? Well, again, we want to show that two sets are equal, and there is a standard way in which we prove two sets are equal, which is if you want to prove that a set X equals a set Y, so let's call this thing X and this thing Y. Well, if you want to do this, then the standard way to prove that X equals Y is to prove that X is a subset of Y and Y is a subset of X. So let's do this. We will start by choosing an element in X and proving that it also must belong to Y. So let's let Z be an element of X. Okay, Z is an element of the complement of A union B. So Z is not in A union B. Okay, if it's not in A union B, well then it can't be in A and it can't be in B. It can't be in either of A and B. Alright, if Z is not in A, then that means Z is in A complement. And if Z is not in B, then that means Z is in B complement. Okay, Z is an element of A complement, it's an element of B complement, so it's an element of the intersection of A complement and B complement. But that's the set y. So we have started with an element of x, any element of x. We've proved that it's in y, and that means that x is a subset of y. Okay, so we've done half of our job. We've proved that x is a subset of y, and we're now going to carry on and show that y is a subset of x, from which we'll be able to conclude that x and y are equal. Okay, so let us now choose an element in y. So again, I'm going to call it z. Let z be an element of y. So y is the intersection of a complement and b complement. If z is in y, then it's both in a complement and in b complement. Okay, being in a complement means that z is not in a. And similarly, z is not in b. Alright, if it's not in a and it's not in b, then it's not in the union of a and b, because to be in the union of a and b means that either you're in a or b or both. Our element z isn't in a or b, so it's certainly not in both a and b, and therefore it's not in a union b. And if z's not in a union b, well, that means that z is in a union b complement. Okay, a union b complement is x. So we've shown that our arbitrary element of y is also an element of x. That means y is a subset of x. Alright, now we know that x is a subset of y and y is a subset of x. Putting those two things together, x is a subset of y and y is a subset of x. So x equals y. In other words, the first of De Morgan's laws really does hold. Okay, I'm not going to prove the second of De Morgan's laws here. You can do it for yourself using the same method, or if you like, you can look at the lecture notes for this video where this proof is written down. So the last thing we're going to do in this video is to look at the double complement law. So the double complement law is just a very simple equation which says that if A is a subset of a set omega, then if you take the complement of A in omega, then what you get back is A again. So A complement is equal to A. Okay, let's try proving this this simple result. I think it's pretty clear, but let's just try and write down a proof. So here's our proof. So if we pick something in omega, let's say W, an element of omega, well then W is in a complement if and only if W is not in a complement, right? The complement of A is everything which is not in the complement of A. So you're in the complement of A if and only if you're not in the complement of A. Okay, well let's just take the same reasoning one step further. You're not in the complement of A if and only if you are in A, because the complement of A is the set of things which are not in A, so the complement of A is the set of things which are in A. I've drawn a cross there, which I shouldn't have done, so let's just correct that. There we go. Now we have that an element in omega is in the complement of A if and only if it's in A, and therefore A and A complement have the same elements. So the same elements means that something is in A if and only if it's in a complement, and if they have the same elements, they're equal. Okay, so that statement's called the double complement law.